In the previous video, we looked at credit ratings, which are a very easy way to get a probability of default, but obviously those are only available for very large firms that are willing to pay the cost of a credit rating certification. For the vast majority of firms, which are small firms, we do not have a credit rating. So when a firm comes up to a bank and asks for a loan, the bank needs to have some internal rating model to assess the likelihood that the firm is going to be able to pay back the loan. So that's what this chapter is about, internal rating models. So the natural starting point is to use the information that we have on the firm, namely balance sheet and income statement information. So the first model to do this was developed by Altman in 1968. Then the model is this very simple model that you see here. So basically what we are going to do is we're going to use the information that is available from the balance sheet and the income statement, so in the form of these ratios here. And we're going to use these ratios in this function that you have here. So for a given firm, you have these numbers here, these ratios. You plug in the ratios in this formula, and out comes a number, which we call the z-score. And then we compare the z-score to a threshold. In this sample of Altman 1968, the coefficients and the thresholds were estimated with these numbers that you have here. So if the number that comes out is bigger than 181, the decision is that this is a good firm and that we should give credit to the firm. Otherwise, if it is smaller than that number, it is a bad firm. Okay. So just to get an idea of the values here, this is actually the ratios for the average bad firm in that 1968 sample, and these are the ratios for the good firm in that same sample. So if you plug in the numbers for the bad firm in the z function, you get this number here, minus 0.26. And again, the decision is that it is less than 181, so you should not give credit to the firm. And likewise, for the good firm, the average number would be something like 487, which is above the cutoff, and so you should give credit to this firm. Okay. So there are some statistical details here that you can skim through this. This model has been improved through the years. So after that initial model, Altman came up with a z-prime score, which is pretty much the same thing, but now the difference is that the previous model required us to use stock market data, and this model is applicable to private firms, so we do not need to use the stock market data. Instead, we replace what was coming from the stock market just by the book value of equity. So same type of idea, you plug the ratios in there, you get the number, and then you make a decision. There's also slightly difference relative to the previous model. Now there is a gray zone in the sense that if the z-score is between this range here, we do not know what to do. And finally, the more modern version of the model is called the z-prime score. And now this is applicable to any firm, be it publicly traded or private or from an emerging market. So this is the current version. This is the same function as before with different coefficients, but with using the same ratios. We call this z-prime. And then this is actually what you will see on the Bloomberg screen, the z-prime. But then for a table we'll see in a second, you need to add to it 3.25, and we call this, just to distinguish one from the other, we call this second version the z-prime standardized. And then you have the cutoffs here to make a decision. Right? So even though this model here does not give you directly a probability of default, it only gives you a decision whether to give credit or not to give credit. There has actually been some work in trying to make a correspondence between this z-score and a credit rating, from which then we could get a probability of default. And that correspondence is given here in this table. Okay. So this example here shows what is the advantage of using this method. And basically the advantage is that it is very simple. So what you have here is a Bloomberg screen, and you can see that they immediately show you the z-score, the initial version, 142. So that's the very first model. You compare this with a threshold of 1.8. And then they also show you the double prime z-score, right, which is this part here before the standardization. Okay, so you can immediately take this number 0.83, add to it that standardization part here, the 325. So 0.8 plus 3.25, that's 4.0 something, 08. And you can come here to the table and get a rating. So 408 to be somewhere in here. So according to this correspondence, the firm is a B- firm. So this is extremely easy to do, right? It took me almost no time to do this because I just need to do the ratios from the firm and immediately get this number. And then it's very simple. And the nice thing about it is that it's relatively accurate. So if you look at the actual rating of this firm on this date was B+, right? So this was the rating that Standard & Poor's did with a lot of work, analysis of the firm and so on. So presumably a more precise assessment of the firm. This shortcut, this z-score, put me in a relatively close range, B-. All right, so that was the old days of credit rating. What we want to do nowadays is not just to say whether a firm is good or bad. What we want to say is how good or how bad. So instead of being just black or white, what we want now is a shade of gray. And depending on that level of riskiness, we are going to charge a spread to the firm that corresponds to that level of risk. So we're not just going to say give credit or not give credit. What we're going to do is we're going to price the credit in accordance to the risk of the firm. So what we are going to do now is to actually estimate directly the probability of default, right? So what we have is the same type of information, and that's what we're going to use. So we're going to build a function that is very similar to these z-scores that we have seen before, in the sense that it's going to be a linear function of some ratios, some financial information of the firm. So now the problem is, can I just do this that I have here and call this a probability of default? Well, the answer is no, right? Because if you just do this linear function that you see here, there is no guarantee that what comes out is a number between 0 and 1, which is what the probability needs to be. So I need to do some more work to guarantee that what I have here is a number between 0 and 1 probability. There are two alternatives. One is called the probit, the other is called the logit, and the logit is the one that turns out to be more used. So what I'm going to do is I'm going to take that f function that I have up there, this whole thing, and I'm going to put it through this transformation, which makes the number that comes out, this p, be indeed a number between 0 and 1. Okay, so whatever the f number is, once I do this transformation, p is always a number between 0 and 1. So how do I estimate the model? So basically what I need is the following. I need to have a sample of firms. I need to know the ratios of the firms at the beginning of the year. So basically I need the balance sheet and the income statement of the firms at the beginning of the year. And then I need to know at the end of the year which firms have defaulted and which firms have not defaulted. Okay? And then what I'm going to do is I'm going to estimate my model. Estimating the model means what? Estimating the model means estimating these numbers here, B0, B1, B2, B3, Bn, all these Bs. So estimate these numbers such that my model gives me the best or the highest probability of actually observing this sample that I have. So more precisely, what I'm going to do is I'm going to build a likelihood function, which is like this. The P is the probability for firm I. The probability is this expression here, which in turn depends on the F function, which in turn depends on the ratios, on the X variables, and on the B's that I want to estimate, right? The Y here is 1 if firm defaulted and 0 otherwise. So if the firm, so only one of these terms, either this one or this one, is showing up. The other will always be, for a given firm, only one of these terms shows up. The other is 1. So suppose that the firm defaulted. So if the firm defaulted, Y is 1, meaning I only care about this term here. So I'm going to estimate the probability of the firm defaulting, which depends on F, which depends on the ratios. For a second firm, suppose that the firm did not default. So if the firm did not default, Y is 0. This term shuts down, becomes 1. And now I only care about this term here. Y is 0, so this becomes 1. So only this part here matters. So 1 minus P is 1 minus the probability of defaulting, which is the probability of surviving, which is what happened to this firm. Okay. So the product across all the firms of these terms, it's going to be the likelihood of observing this particular sample. So I will maximize this joint probability by picking the parameters, by picking betas, B's, B0, B1, and so on. Okay. So instead of maximizing this, what we typically do is we maximize the log of this function, the log of the likelihood, and instead of a product, we have a sum, as you see here. Okay, and but the application is relatively simple. You can do this in Excel, right? So just for reference, if you later work with these models in reality, this is a very good paper to read, because they did a massive amount of work testing all sorts of different variables. So it's a good reference to see what variables nowadays work well. Okay. So finally, once we have a probability of default, what can we do? We can use it to price the loan. As we were saying, we have a firm that comes up to the bank. The firm asks for a loan, and the purpose of these models is to estimate the likelihood that the firm will survive or default, and given that probability, say what is the price of the loan, meaning what is the spread that the bank is going to charge to the firm. So the idea is the following. Banks typically worry about their risk-adjusted return on capital, which is this ratio that you see here. This is the revenue that we get from the loan, typically a rate plus some spread times the amount of the loan, minus the cost of getting the money to lend it to the firm, and this would be something like the floating rate times the amount of the loan. So this is the funding cost of the bank. And then we have the expected loss, which we have discussed in the initial chapter. So the expected loss is the probability of default, and this is where the model, the Logit model, comes in. The number that we got from the previous explanation comes in here, the probability of default. This is the amount of the loan, the exposure, and this is the loss given default. Right? And then we're going to divide this by the amount of capital that the bank has to have to grant the loan. Okay. In Basel I, this was just a very simple procedure. It was just 8% of the amount of the loan. Okay, and in more recent Basel agreements, this has been changing, but we are going to abstract from that. Whatever that number is, we will just plug that in here. But we don't want to be talking about bank regulation here in this course, so we'll just use this simple first approach of 8%. So basically what the bank needs to do is to find what is the minimum spread to charge on the loan. And the minimum spread would be such that the risk-adjusted return on capital is at least equal to the return on equity that the shareholders demand. So if you solve this with an equality sign here, you'll find the indifference, the minimum spread that the bank will charge to the loan. So it depends on the return on equity times the capital that the bank needs to put aside, the shareholders need to put aside, plus the probability of default that we got from the Logit times the loss given default. Okay, so that's it. Thanks.